Hi, and welcome to another video on integration by parts. So hopefully you've gone through the beginning of the by parts formula, where that comes from, because we know that we're basically starting from the derivative of the product rule and then kind of undoing that. So the main idea in that first video was trying to figure out which part of the integrand is our u and which part is our dv. So which part are we integrating and which part are we differentiating? And remember, the whole goal is that our new integral looks a little bit easier to integrate than the beginning one. So let's take a look at something like this. This is a definite integral, so we will have a little bit more work at the end because we will have to put our bounds in and get an exact answer. It also makes it a little bit more checkable using technology, which might be helpful. So in here, we have that liate. I'll kind of remind you of that right now. This is the order of who to try for who is your u. So the first L stands for logarithm, natural log or logarithm. I is the very second piece, which is inverse trig, because we know it's a little bit easier to take the derivative of inverse trig than it is the antiderivative. So let's see how this is going to look. So I'm going to say u is this inverse tangent of x. So then dv will be the leftover part of the integrand, which is just that dx. Okay, so now on the left-hand side, again, we're always doing the derivative headed down. So if you're given u, you need to find du. So we should remember our inverse trig derivatives from Calc 1. So this was just 1 over the sum of squares, so 1 plus x squared. Don't forget your dx. And then moving across, I'm going to, on the right-hand side, do the antiderivative going down. So the antiderivative of dv is v, and antiderivative of dx turns into x. And then if you set it up this way, your by parts formula calls for uv, no more antiderivative, minus the antiderivative of v du. So it'll always sort of look like that. So this antiderivative is going to be the same thing as x times inverse tangent of x. And I'm strategically writing it like that. I know that I'm multiplying these two things together, inverse tangent of x and x. But if you write them right next to each other like this, there's a couple opportunities for error in there, like multiplying those x's together or not seeing what they really are. So I just don't write it like that. I just write basically x is a coefficient of inverse tangent of x. And then minus the antiderivative of v du. So when you multiply those, you're going to get x over 1 plus x squared in the denominator dx, just like that. Now, because I'm still in x's, I can still have the bounds, which were a lower limit of 1, lower limit of 0, upper limit of 1. So my bounds went from 0 to 1. Still same variable, so I can keep my bounds the same. So we've written out our by parts formula there, and I am going to have to evaluate this x inverse tangent of x at my bounds using the fundamental theorem of calculus. So it looks something like so. You could evaluate at your bounds once you're all the way done integrating. So that's what we'll do. So now I should be able to take this new integrand here, x over the quantity 1 plus x squared, all times dx, and I should be able to recognize how to integrate that. And hopefully you see that that's a u substitution. So u substitution can get pretty tricky when you just had a u and a dv for your by parts. So I'll just do a w substitution. You can call it any letter you want. I just won't use u, v, or x in this case because I've already used those. So I'm going to use w. So I'm going to say w is that 1 plus x squared. So dw is 2x dx. So what we hopefully have learned throughout our integration so far is that this sort of u substitution idea does take place fairly often, where all I need to enter in here is a coefficient of 2. Then I have my dw over w. But if you multiply the inside by 2, you have to multiply the outside by a half because you shouldn't be changing the value of your integral. You're just changing the way that it looks. Again, we do this all the time with common denominator type things, right? We multiply by what we need, but we have to make sure we're always multiplying by a factor of 1 so we're not actually changing the value. So I will write what I have left, but I'm not going to put bounds on this step because not everybody actually writes this part down here. This is the W, this is the dW over W, which will turn into natural log. I do have bounds here. If you would like to change them, you can. One reason that I might not change them is because I also have to put my 1 and 0 into that first part, so I'll do that all at the same time. So what I really do have is x times inverse tangent of x, and then this antiderivative will become minus 1/2 natural log of w. That's dw over w integrates to natural log of w. So this will become 1/2 natural log of, and if you put your w back in terms of x, 1 plus x squared. And then I can just evaluate the whole thing from 0 to 1. So I'll put 1 in. So 1 times inverse tangent of 1 minus 1/2 natural log of 1 plus 1 is 2. And then I'll put my 0 in. So that makes 0 inverse tangent of 0. So that will be 0 minus 1/2 natural log of 1. And natural log of 1 is 0. So yes, that whole piece becomes 0. And we should know something about inverse tangent of 1. So we're looking for the angle where the opposite over adjacent divide out to be the same, or divide out to be 1. So they are the same at that 45-degree angle, or pi over 4. And I don't need absolute value bars on 2 technically because it already is positive. And so I could certainly check this using technology, just making sure, again, technology is going to spit out that decimal answer or that rounded answer, and just check that they're equivalent. Okay, here's another example, and we're going to use a W substitution here again. So I think that one piece that gets missing when we're doing such detailed calculus is the idea of zoom in and zoom out. So what I'm hoping that you can do when you look at a calculus problem, and this is truly at any level, is be able to also step back and sort of zoom out and say, what is the problem asking me to do, or what am I trying to find, or what do I already know? But it's that idea of kind of zooming out and just looking at it from a little bit bigger of a lens. When we're so zoomed in for detail and, oh, I know, I'm going to let u equal this and dv equals this, and we forget to look at kind of that bigger picture, we can miss some sort of obvious maybe connections that'll make my problem a lot easier to work with algebraically. So this is one of those examples. I do have natural log of a function, which absolutely in the Iliate should maybe come first with who should be my u, and I'll go through that. But what I also notice, and hopefully you notice too, is that cosine of x and sine of x have a derivative relationship to each other. So I'm going to first do a w substitution. And again, I'm not using u or v because I'm going to use u and v for my by parts formula. So I'm just going to turn this into w. So what I'm going to say is if w is cosine of x, then I'm replacing this part with a w. So it'll just look like natural log of w. Okay, well, I have to turn everything else then in terms of w. So let's see. dw, derivative of w, is negative sine x dx. Well, that might make my problem a whole lot easier, actually, because if you multiply inside by a negative and outside by a negative, you're multiplying by 1, so you're not changing the value, you're just changing the way that it looks. And then I can use the negative sine x dx, that'll turn into dw. And the other part is just natural log of w. So it'll look like this, negative, and then the antiderivative of natural log of w dw. And I don't have bounds, but if I did, I would absolutely change them to w bounds at this point. Okay, so now I'm going to go through my by parts. So 1 part, the natural log of w, I'll let be my u since that's a natural log. I want that to be my u. And then the only thing left in my integrand is dw, so that will be my dv. And then again, my setup always looks the same. So on the left, I'm doing a derivative. So du is 1 over w dw. Hopefully you remember that derivative. And on the right, so going from dv to v, I need to do an antiderivative. So that's just w. Okay, so again, don't forget about this negative out front. If you are like me and you often forget about coefficients or negatives, or you have trouble sometimes getting a negative wrong, I'm going to make a suggestion right now. I'm not going to leave it out front of everything. Instead, I'm going to assign it here to the natural log. So here, negative natural log of w. So that changes my du to be negative 1 over w dw. Now I've used it in my problem, and I don't have to worry about later remembering, hey, oh yeah, I had that negative out front. I need to distribute that to everybody. So I already have accounted for it. It'll just be a part of my problem. So here's my u times v. Now, when you multiply negative natural log of w times w, again, if I write it like this, technically that's what we're saying and doing, but the tendency might be to multiply those w's or combine them together somehow. So I'm going to write that w in front of the natural log. So w times natural log of w. So this w I'm just going to put as a coefficient instead of writing it after it. Again, 2 times 3 is equal to 3 times 2. You're just using the commutative property of multiplication. So there's my uv minus the antiderivative v du. So it's w times negative 1 over w dw. And I did write the whole thing down because some of us do sign changes in our head, and then it's hard to follow our work later and find errors later. Okay, so what do I have now? My first term remains unchanged. And then this will become plus, because I have minus and negative. W's divide to 1, so I'm literally just integrating 1 dw, which will just turn into w. Now, don't type this into any, system and check your answer because it's going to be wrong, because remember, our problem started in a variable of x, so everything was defined with x's. We changed it to be w's, so we do have to go back and put it in terms of x. So w being cosine of x, so it'll be negative cosine of x times natural log of cosine x. That's my negative w natural log of w. And then plus w, which was cosine of x, plus c. Okay, so that wasn't too bad. Again, that's that idea of zooming in or zooming out. Let's do 2 more. So x times tangent squared x dx. If I'm integrating this, I kind of think of this liate. I don't have any natural logs. I don't have any inverse trig. Ooh, but I do have something algebraic. And what we mean by that is a basic power of x, perhaps. I won't say polynomial because sometimes those powers of x might be negative, but as you go through, you'll see. But a lot of times they are just your polynomial type expression. So there's x. So I'm going to let that be my u. And my dv be tangent squared x. Ooh, but hold on. Do we know how to integrate tangent squared x? Oh, I do. Because we have 3 trig identities. They are the Pythagorean identities. So are you familiar with the Pythagorean identity? Cosine squared plus sine squared is 1 of any angle, as long as your angles are the same. I can take that main identity and divide through by cosine squared x. So I get 1 plus sine squared over cosine squared is tangent squared x equals secant squared x. And if I wanted to quickly derive the third one, I could. I would just take the original and divide through by sine squared x. So cosine squared x divided by sine squared x is cotangent squared x. Sine squared x over sine squared x is 1. And the reciprocal of sine squared x is cosecant squared x. So if I needed all three, I could certainly derive them from the basic one. Okay, so I'm going to look here at this middle one, and what we hopefully gathered from our Calc 1 course was that because I can integrate secant squared x, we know the antiderivative of secant squared x is tangent because the derivative of tangent is secant squared. Great. So because I can integrate secant squared, I can also now integrate tangent squared because I can say tangent squared x is the same thing as secant squared x minus 1. So I'm going to back up just a little bit here in this problem, and I'm going to rewrite tangent squared x and say that this integrand would be x times, and instead of tangent squared x, I'll say it's secant squared x minus 1. So I'm going to wait just a minute on the by parts formula, and I'm going to rewrite my antiderivative. So if I distribute that x in there, I have x secant squared x, and then just minus x, and it's all with respect to x. Well, I can integrate x all day long. So I'm going to split this up into 2. So it'll be x secant squared x dx minus the antiderivative of just x dx. Now make sure when you rewrite them that you do have the dx portion in each antiderivative because that becomes very important. Okay, so now this x secant squared x is exactly what I was talking about earlier. This is the by parts part. Well, the algebraic part, right, is x, so that will be my u. And now my dv, the rest of that integrand, will be secant squared x dx. And now I'm good to go. So this is sort of that idea, again, of kind of zooming in and zooming out. One of your parts you hope is easy to differentiate. And when I say easy, I just mean it's a technique that we know. And one of the parts should be easier to integrate. And at first, you might not think something like tangent squared is easy to integrate. But again, we got to go back to our Calc 1. Oh, it's just a quick rewrite, and now I can integrate it. Okay, so I'm doing the left. I will do the derivative. So if I have u is x, du is just dx. And on the right, I'm doing this antiderivative. So the antiderivative of secant squared x is tangent of x. Okay, so again, I can't forget to integrate x. So I kind of am going to bubble that because that has nothing to do with my by parts that I'm doing right now. So uv, so this whole thing is going to equal uv minus the antiderivative v du. So tangent of x dx. And I'm going to carry my other antiderivative down so I don't forget it. Okay, so the first term is done. Now, tangent of x, some of you may have memorized its antiderivative. It comes from the fact that this is sine x over cosine x. So I could do a u substitution or a w substitution if I need to. But again, some of you may have memorized this. So if w, so if I'm going to take this off to the side here. So if you let your denominator be a w, then dw is negative sine x dx. So I literally have, if I put a negative in and a negative out, because negative times negative is positive, I literally will have dw over w just with a negative out front. So that becomes negative natural log of cosine of x. Like so. Don't forget your absolute value bars. So I'm going to transfer that over here. So because it would be a negative, now this is going to turn this term into a positive, right? Negative, negative. And then integrate x. So x squared over 2 by power rule. Don't forget your plus c, and you are done. Okay, last one of this video, and then what I would encourage you to do is to look up the next video, because this is not necessarily a mistake. I'll get this out of our way. Number 5 is going to be done 2 times. Number 5 is going to be done here in just a standard biparts way. And then I'm going to show you in the next video some tabular integration examples. So I'm going to do the same integral again and just show you maybe a little easier organization for this antiderivative. So here we go, by parts. And this is a pretty standard by parts. So my algebraic, right, will be my u. So I'm going to say u is x squared. Therefore, the dv is sine 3x dx, the rest of my integrand. Because in Liate, you know, trig comes pretty far at the end. So, but algebra is not that much higher. But okay, so the derivative of u, right on my left, I'm going to do the derivative. So the derivative of x squared, 2x dx. And on the right, I'm going to do the antiderivative. So antiderivative of sine 3x. Well, we know it's going to turn into some form of cosine 3x because, again, you're never allowed to change a base or an angle when you're just doing a standard derivative or antiderivative. And I know sine and cosine become each other. So now you need to think, does it need to be negative? Well, I think of it in a derivative fashion. So since the derivative of v should get me dv, and derivative of cosine is negative sine, I do need a negative here. And then if I were doing the derivative of sine 3x, I would need to multiply by 3. And I'm doing the antiderivative, so I'm going to divide by 3. So I'll repeat that again. If you have something like antiderivative of, let's do e to the 7x dx. Well, we know this is going to become itself, so it's e to the 7x. If I were doing its derivative, I would have to multiply by 7 for that chain rule. So antiderivative, I will have to divide by 7. Okay, so hopefully that makes that 1/3 make sense and why it's negative. So this antiderivative will be uv, and I'm going to write the negative 1/3 and then the x squared, then the cosine 3x, minus the antiderivative of v, and I'll just write it down, then I'll make it look better maybe on the next step, du. And I will maybe combine some terms together and see if this integral looks a little bit better or more doable than my original. So this will become plus, and I'm going to leave my coefficient in. I'll share with you why here in a second. So I'm going to say that it's 2x over 3 cosine 3x. Right, because 2 times the third gives me 2/3, and it's just x cosine 3x. Okay. I'm going to compare this to my original. I still do not have an integration technique. Think of a technique that you would have learned, for example, in Calc 1. I don't have an integration technique to complete that antiderivative, but did it get easier or a little bit more workable than my original? And what we can notice is that sine and cosine, right, the original used sine, this one now is cosine, are just gonna, and no matter how many times you do the antiderivative, they're gonna flip-flop back and forth between sine, cosine, sine, cosine, sine, cosine. Okay, so that's not necessarily changing all that much. And then now, do you see I had a power of x squared, and now I only have a power of x? So chances are, if I do by parts one more time, I'm breaking down that algebraic expression or factor or part to be, now it's linear. Well, if I do the derivative one more time, it will become a constant coefficient. And that I should be able to integrate. So I'll do it one more time. I'm going to make u still be the algebraic piece, so it's 2/3 x or 2x over 3, however you prefer to write it. So your dv has to be the rest of that integrand, which is cosine 3x dx. This is my suggestion to you. You can certainly take it or leave it. I tend to lose coefficients when I take them all out front, or negatives, things like that. I don't want to lose anything. So I'm going to not bring the 2/3 out front. I don't do that. I leave it in my integrand and make it be a part of my u so that it will be a part of my by parts formula, and then I never have to worry about remembering it later. So it's just a little added bonus for me. So now my du is 2/3 dx, right, that linear derivative. And my antiderivative, well, the antiderivative of cosine of an angle will be sine of that angle, because derivative of sine is cosine. And then instead of multiplying by the derivative of that angle, I'm going to divide by it. So I'll divide or multiply by another 1/3. Okay, so I'm going to copy down my first term so I don't lose it, right? This has got to come down. And then I had a positive in between. That's one thing that if you make an error or if you're not getting a question right, you certainly want to look right there at that sign, because chances are you didn't distribute a negative correctly or something went wrong with that. Okay, so now it's u times v. So if I multiply those together, I'll get 2/9 times x times sine of 3x. And then it's minus the antiderivative of v du. And if I rewrite just that part of the antiderivative, it will be a negative, and it will be a 2/9 sine 3x dx. And I can absolutely integrate that piece. So for my final answer, I will copy down the first two terms carefully, because this is sometimes also where we make an unwanted or unforced error. Okay? And then if you antiderive sine of an angle, you will get cosine of the angle. And then I'm going to have to divide by 3 again. So this will become 2/27. And then since the derivative of cosine does get me negative sine, this will be a plus, because the antiderivative of sine is negative cosine, so it'd be a negative negative. All right, that's it. And again, I'm going to, in the next video, do this problem with far fewer steps, which just removes maybe some opportunity for error. But you can certainly do by parts over and over and over again if the integrand is if it's necessary for that integrand. So oftentimes if you have a power like x squared or x cubed or things like that, you definitely might have to do by parts a few times. So I will go through a few of those examples in the next video. I hope you found this helpful. Thanks for watching.